Analog and Digital Electronics. This is Swathi, working as Assistant Professor in Institute of Aeronautical Engineering in the Department of Electronics and Communication Engineering. In this lecture, we'll discuss about the load line analysis of PN junction diode. Before going to the topic, first of all, why we are studying this load line analysis? So load line analysis is the graphical analysis of VI characteristics of nonlinear electronic circuits. So nonlinear electronic circuits are the circuits which includes nonlinear devices like PN junction diode or transistor. So why we need to go for this load line analysis? Because these devices, PN junction diode and transistor, are said to be nonlinear devices because the characteristics of this PN junction diode and transistor are nonlinear, means which does not obey the Ohm's law. So here are the characteristics of PN junction diode under forward bias characteristics, which are exhibiting nonlinear characteristics. So first of all, let us define the load line. Load line is a straight line drawn on the characteristic curve, that is a graph of current versus voltage in a nonlinear device like diode or transistor. So let us consider the circuit, basic circuit, which includes the nonlinear device, that is a diode, PN junction diode, which is having a voltage source represented with Vs and a resistor in series. So we can take this resistance as a low resistance and in series with a PN junction diode, and the voltage drop across this PN junction diode is represented with Vd. And the current flowing through, as all of these are connected in series, so the same current will be flowing through this circuit, which is represented with Id. So Vd is a voltage drop across the diode and Id is the current flowing through the circuit. And these are the characteristics. This blue line shows the VI characteristic curve of PN junction diode under forward bias condition. Whereas this is the straight line which is drawn on the characteristic curve, and this straight line is named as load line. How to draw this load line? So for that, first take the KVL for this equation, that is Kirchhoff's voltage law for this loop. This is forming a closed loop structure. So whereas the closed loop structure can be explained mathematically by writing a Kirchhoff's voltage law equation. So by applying the Kirchhoff's voltage law, the equation we can obtain it as Vs minus, that is the input voltage, minus, as the current flowing through this circuit is Id. So the voltage drop across the resistance R is given by Id into R minus Vd, which is nothing but the voltage drop across the diode, is equals to 0. So this is the equation which is governing the circuit, that is representing the mathematical equation representing this simple diode circuit. So now, in order to draw a straight line, we need to find out points of intersection with the x-axis and y-axis. So from the above equation, so we can see that here you can take this as Vs instead of Vdd. So as we have got the equation as Vs is equals to, if I take these two terms to the other side of equal symbol, so I will get this as Vs is equals to Id into R plus Vd, and from this equation I can even write down the equation for current Id, that is equals to Vs minus Vd divided by R or else RL. So here now, this is the current equation. From the above thing which we have got from the equation 1, we can obtain the current equation as we can obtain the current equation as I is equals to or else ID is equals to Vs, which is the input voltage, minus Vd divided by R. So here now, as I want to find the intersection points of a straight line which is to be drawn on the characteristic curve with the x-axis and y-axis. So let us take the equation, first equation, Vs is equals to Id into R plus Vd, and in order to find out a point of intersection of the straight line with x-axis, point of intersection with x-axis. So as we are locating a point on x-axis, so we can say that if you observe the characteristic curve, we have drawn it with respect to voltage and the current, where the voltage is taken as voltage drop across the diode and current is the current flowing through the diode or else the current in the circuit, that is ID. By taking Vd on x-axis and Id on y-axis. So in order to locate a point on x-axis, we need to consider the value of y-coordinate as 0. Y-coordinate means current, that is Id. So to identify or else to locate the point on x-axis, just assume, that is let y-axis, that is Id, must be considered as 0. Now substitute this one in the above equation. So I will get it as 0 into R plus Vd. So that means by taking this, we can obtain that Vd is equals to Vs. So means here we can locate a point A in which x coordinate value is Vs, whereas y coordinate value is 0. This is point A. Similarly, I want to locate a point on the y-axis, point of intersection of a straight line, point of intersection of a straight line with y-axis I want to find. Point of intersection with y-axis. So when I'm finding a point on the y-axis, definitely I should consider the x coordinate value as 0. On x-axis I'm taking Vd, so and hence let Vd is equals to 0, and from the above equation Vs is equals to Id into R plus 0. So this implies that here I want to find out Id value. So Id is equals to Vs by R. So this is the y coordinate value when I'm considering x value as 0. So this is representing a point B which is to be located on y-axis, which is given by x value is 0 and y value is to be taken as Vs by R. So these are the coordinate values that we have taken. So now just locate them on the characteristic curve. So here this is the point A, that is on x-axis, where y coordinate value is taken as 0, Vs comma 0, and this is point B where x coordinate value is taken as 0. X coordinate means 0 comma Vs by R. So now join these 2 points. This is point B and this is point A. Now by joining these 2 points, I can draw a straight line. So this straight line which is joining point A and point B and which is extended onto the Vi characteristic curve of PN junction diode is said to be load line. The straight line drawn on the voltage versus current characteristics of a nonlinear device, here my nonlinear device is a PN junction diode, is known as load line. When I draw a straight line onto the Vi characteristic curve of PN junction diode, it is intersecting with that PN junction diode characteristics, and the point of intersection of load line with the Vi characteristic curve is said to be operating point. So operating point of a nonlinear device is defined as the point of intersection of load line with the Vi characteristic curve. So here now let us find the value of operating point. So that is, let us represent that voltage at that particular point as VDQ, whereas the current at that particular point is IDQ. So this operating point is also known as quiescent point, which is nothing but the intersection of load line, and it is a load line with respect to the VI characteristics of a nonlinear device, which is represented with Q, which is given by VDQ gamma IDQ. So these are the corresponding current and voltage flowing through the diode and at the point of intersection of load line with the VI characteristics. So now here, so this is how we can draw a load line on the VI characteristic curve of a nonlinear device. So which is used to explain or else analyze the nonlinear behavior of a nonlinear device like either diode or transistor. So let us find the slope of the straight line which is drawn onto the VI characteristics of PN junction diode. How to find the slope? So for that, let us consider the equation Vs is equals to ID into R plus Vd. Let us divide this equation. With divide by R on both sides. Divide by R on both sides. Then we'll get Vs by R is equals to ID plus Vd by R. So now we know that a straight line is mathematically represented with an equation y is equals to mx plus c. On y-axis, what we are taking? We are taking current, that is G, and on x-axis we are taking voltage V. Let us rearrange this equation in this form. Y is equals to mx plus c. So y is ID. So I want to get ID here. So here this one will give you, this term will go this side. So minus Vd by R plus Vs by R. So here ID is Y and Vd is X. So now let us compare this equation with the general straight line equation, that is y is equals to mx plus c, in which y is a value, and here what is that? That minus 1 by R will be the slope, where m represents the slope, y represents the y-axis, and x represents the x-axis, and c represents the intercept. So here now by approximating this one with y is equals to mx plus c, I can say that the slope is equals to minus 1 by R. And intercept value is Vs by R. So this is the slope of the straight line which we have drawn on the VI characteristic curve of PN junction diode. So the slope is minus 1 by R. That means it is having a decreasing slope. So even if you observe the straight line which we have drawn, it is also having a slope which is negative because it is decreasing. As the voltage is increasing, the current is decreasing. That means we have a negative slope, and the slope of that line is minus 1 by R. So here, as the slope is a function of load resistor, which is also considered to be a load resistor. So if there is any change in the load value, definitely there will be a shift in the load line, and hence there will be a shift in the operating point. So for example, if I consider RL is increased, if I consider RL or else R is increased, so then what happens to the slope? If RL is increased, then the slope M is equals to minus 1 by R, so will be decreasing. Minus 1 by R, that will be decreasing. So here if you draw, for example, if I consider R value initially, if I consider the R value as 10, so for example this case, then the slope value is minus 1 by 10, that is minus 0.1. For example, if my load resistor is reduced to 1 ohm, then my slope will become 1 by minus 1 by 1. So which is equals to 1. So what is happening? Here the slope is increased from minus 0.1 to minus 1. If I increase my resistance to 100 ohms, then what happens? M is equals to minus 1 by 100, and hence the slope will become minus 0.01. So that means if I have a slope of this, that means if I have a resistance of 100 ohms in series with the resistance, then my slope will be reduced. If that slope is reduced, so Vs by R, what is this Vs by R? Vs by R value will also be reduced because I have considered Rs is equals to 100. So that means denominator is increased. So what happens to this one? This value will be reduced. So that means I'll get the point somewhere here. Okay. And here, if I join this point again with the point A, so I can get my new operating point somewhere here. That means with the change in the load resistor, the operating point, the load line will be shifting. If the resistance is increased, the load line shifts downwards. If the resistance is increased, then the load line will be, if the resistance is increased, load line shifts downwards. If the resistance is decreased, load line will shift upward. And hence the operating point will also shifting. So this new operating point can be denoted as VDQ dash comma IDQ dash. So this is the effect of load line. So that means whenever we are changing the load resistance, it changes the slope of the load line, and hence the operating point will and hence we can also observe a shift in the operating point, which describes the behavior, nonlinear behavior of the device like diode. So the region below the operating point is said to be linear region of operation, and above the operating point is said to be non-linear region of operation. So and hence the linear mode of operation and non-linear mode of operation will be completely depending on the load resistance or else resistance connected in series with the diode. So this is about the load line analysis, which is to be done for analyzing the nonlinear behavior of a nonlinear electronic circuit. So, next up, we'll discuss what is the relation between the temperature and the VI characteristics of a PN junction diode. How the temperature is affecting the VI characteristic curve. So that is a topic. So here, let us observe these VI characteristics. And first of all, the PN junction diode can conduct at a given voltage, applied voltage will definitely depend upon the temperature, that is operating temperature. So if there is any increase in the temperature, what happens? So increase in the temperature is nothing but it gives the thermal energy to the electrons or holes. Thermal energy of the majority charge carriers will be increased with the increase in the temperature, due to which the electrons or free charge carriers acquires more velocity. With that increased velocity, these electrons or else free charge carriers will collide with the atoms, and hence the covalent bonds will be broken. So once the covalent bond is broken, so what happens? Here the more number of electron hole pairs are created. And due to this increased number of majority and minority charge carriers, a large amount of current will be flowing through the diode. That means whenever there is an increment in the temperature, there will be an increment in the current flowing through the diode. This is because of the thermal energy, which increases the velocity of majority and minority charge carriers, and hence they will collide with the atoms and creates more number of majority and minority charge carriers. finally the amount of current flowing through the diode will be increasing. And hence we can say that whenever the temperature is increased, so here if you observe this curve, this is the VI characteristic curve at temperature T is equals to 25 degrees centigrade. If I increase my temperature to 75 degrees centigrade, for even a less voltage applied, there will be a more amount of current flowing through the diode due to the thermal energy, which creates more number of majority and minority charge carriers, and hence current will be increased than the previous case, that is than at the 25 degrees centigrade. And hence the characteristic curve will be shifting towards the origin. This happens both in case of forward bias condition and even in case of reverse bias condition. So these upper curves are representing the variation of characteristics, VI characteristic curve with respect to the change in or else increment in temperature. So this lower curve represents the variation in the reverse characteristic curve of PN junction diode with the increment in the temperature. So here also the same thing. If the temperature is increased, so there will be more number of minority charge carriers created, and hence more current will be flowing through the diode due to the minority charge carriers, and hence the curve will be shifting towards the origin. And we can also say in other words, in case of with the increment in temperature, the VI characteristic curves under forward bias will be shifting upwards, and the VI characteristic curve under reverse bias will be shifting downwards with respect to the increment in temperature. So this curve shows the temperature dependence of VI characteristic curve of PN junction diode. This happens because the diode the capacity of diode conduction will majorly depend upon the temperature, even there is a change in the applied voltage. So let us now discuss the breakdown mechanism in PN junction diode. So as we all know, in case of reverse bias, the PN junction diode, the current through the PN junction diode will be due to the minority charge carriers, and these minority charge carrier are very less in number, and hence under reverse bias condition there is a little amount of current flow through the diode which is of the order of which is of the order of nanoamperes or microamperes. Nano or microamperes. As you all know, nano is 10 to the power of minus 9 amperes and micro is the 10 to the power of minus 6 amperes. So there is a little amount of current flow through the diode and in case of reverse bias condition. But if you still further increase the reverse voltage applied to the diode, the junction may break down and hence more current will be flowing even for a constant voltage applied. So that is called as breakdown. So that means if you increase the voltage more than 5 volts, let us say, then there will be a breakdown occurring in the junction, in the PN junction diode, which leads to a rapid increase in the current even for the constant voltage applied. So there are two types of breakdown mechanisms in a reverse biased PN junction diode. Those are avalanche breakdown and Zener breakdown. So the avalanche breakdown mainly happens in lightly doped diodes, lightly doped PN junction diodes, whereas Zener breakdown occurs in heavily doped PN junction diodes. Heavily doped PN junction, the example of heavily doped PN junction diode is Zener diode. Zener diode is also a PN junction diode, but it is heavily doped, in which we can experience Zener breakdown, whereas in a lightly doped PN junction diode, that is a normal PN junction diode, we can experience avalanche breakdown. So what is this avalanche breakdown and Zener breakdown? Let us see now. So before going to that, so first of all, I am talking about lightly doped diodes and heavily doped diodes. What is the difference in case of heavily doped and lightly doped? So here you can observe that the width of the depletion region is inversely proportional to the doping concentration. Is inversely proportional to the doping concentration. Lightly doped means number of impurity atoms added is less, whereas heavily doped means number of impurity atoms added is more. That means here in lightly doped diodes, the width of the depletion region will be more. Width of the depletion region will be high, or else is wider. Whereas in heavily doped diodes, as I told you, the width of the depletion region is inversely proportional to the doping concentration. As a diode is heavily doped, these Zener diodes will have very thin depletion region. This point you have to remember. And here we already know that due to the depletion region, there exists an electric field intensity near the junction. So where we know the formula of that is electric field intensity is E is equals to V by D, where V is the applied potential, and D is the width of the depletion region, or else distance of the depletion region. Width or distance of depletion region. So now, what happens in case of heavily doped diodes? What is the electric field intensity I am talking about? So, in lightly doped diodes, so when the diode is lightly doped, as you know that the width of the depletion region will be high. As this value is more, so what happens to the electric field intensity? It will be less. E value is less. That means it is that near the junction we have less electric field intensity. Whereas in heavily doped diodes, so this point you have to remember, in heavily doped diodes, as a depletion layer width is very thin, so that means this is reduced, means what happens? Electric field intensity will be more. That means in heavily doped diodes, we have intense electric field near the junction. Okay, electric field intensity is high. That means I can say that in a lightly doped diode, the electric field intensity near the junction will be less, whereas in heavily doped diodes, we have intense electric field near the junction. Now let us see what do you mean by avalanche breakdown and what do you mean by Zener breakdown. So here, this is a PN junction diode. You can observe here, this is a PN junction diode which is reverse biased here. How can I say that this is reverse biased? This negative terminal of the battery is connected to the P-type material, which is positive type, or we can also call it as anode, and positive terminal of the battery is connected to the cathode of the diode. That means negative N-type region of the diode, which makes the diode reverse biased. So what happens under reverse bias condition? So all the majority charge carriers, which are holes in the P-type material and electrons in the N-type material, are attracted by the battery terminals of the battery, and hence all the majority charge carriers will be moving towards the terminals of the battery. Whereas the minority charge carriers, which are electrons, which I have represented with orange color. So these electrons will be trying to cross the junction. So one thing you have to remember, whenever the majority carriers are moving away from the junction and they will be colliding with the atom, they will be recombining with the electrons, and electrons will recombine with the holes, and holes will recombine with the electrons, leaving the donor atoms or acceptor atoms uncovered, which increases the width of the depletion region. So this is nothing but my width of the depletion region, which is increased due to the movement of majority charge carriers away from the junction, leaving the donor atoms in the N-type region and acceptor atoms in the P-type region uncovered. These will be joining with the depletion region. These uncovered immobile ions will be joining with the depletion region, and hence the width of the depletion region will be increased. So that means under reverse bias condition, we have a wider depletion region. And now what happens? So as the minority charge carriers will be crossing the junction, there will be a little amount of current flow through the junction, that is due to minority charge carriers, which is also called as leakage current, reverse leakage current. So here now what is happening, if you further increase the reverse voltage applied, what happens if we further increase the reverse voltage applied? So due to this increased applied voltage, so here the free electrons acquires more energy with the more reverse voltage applied, and they will increase that free electrons will increase its velocity. With that increased velocity, they will, when the minority charge carriers are moving across the junction, during that journey, they will collide with the atoms. So here I have shown the atom here. So they will collide with the atoms, and hence breaking the covalent bonds, creating new electron hole pairs. So one electron collide with the atom will create a electron hole pair, means increasing the number of majority and minority charge carriers. So if you further increase this reverse voltage, these newly generated electron hole pairs will again increase their velocity, and then with that increased velocity, they will again collide with the atoms and creates furthermore electron hole pairs. So due to these collisions, due to the applied reverse voltage, intense electric field is generated, with which electrons acquire more energy and hence increases their velocity and collides with the atoms. With that collision, new electron hole pairs will be created, and these will again acquire the velocity, the kinetic energy, and hence increases the velocity and creates furthermore electron hole pairs. That means multiples of free charge carriers will be generated. So the process of generating number of electron hole pairs or else free charge carriers is called as avalanche multiplication. And due to this avalanche multiplication, more number of minority charge carriers will be crossing the junction, which increases the reverse current. And beyond a point, there will be more number of electron hole pair created due to that avalanche effect, and hence more current will be flowing, which may destroy the junction completely, and that is called as avalanche breakdown, which increases the current rapidly even for a smaller change in the voltage. So this is avalanche breakdown. So avalanche breakdown is due to the generation of multiple free charge carriers due to the collisions, and hence more current will be flowing through the junction due to the minority charge carriers, and which may further destroy the junction, and hence more current, as a junction is destroyed, so the minority charge carriers can easily cross the junction and more current will be flowing through it. So this is called as avalanche breakdown, and the voltage at which the breakdown occurs is known as reverse breakdown voltage. So in case of as I told you that in lightly doped diodes, this avalanche breakdown happens. So when a breakdown happens in a lightly doped diodes, that means when avalanche breakdown happens, we cannot recover, that means the diode cannot recover its original position. Once it is damaged, we cannot use it further. So this is about avalanche breakdown. Now coming to so this is the mechanism, what is happening in the avalanche breakdown. So here, these are the atoms. So here, due to the heat, these charge carriers will gain kinetic energy and collides with the atoms so that more number of electron hole pairs will be created, and these further collides with the atoms, breaking the covalent bond, creates further electrons. So this diagram shows the collision of electrons with the atoms, which creates further electron and hole pairs. Now coming to the Zener breakdown. So Zener breakdown happens in heavily doped diodes. So as I already told you that in heavily doped diodes, the depletion region is thin. So if you compare with the previous diagram, we were having wider depletion region in case of lightly doped diodes, whereas this is a heavily doped diode and hence the depletion region is very thin. So as the depletion region is very thin, we have intense electric field near the junction. That means this electric field is very high. So here, this electric field is enough to pull out the electrons from the covalent bonds and to participate in the conduction. So the strong electric field pulls the valence electrons from the ions. So from the ions, it can easily break the covalent bonds so that it can pull out the electrons from the valence shell, and hence they can participate in the conduction. So that means in Zener, in heavily doped diodes, the intense electric field which is existing near the junction is enough to pull out the electrons from the valence band. So as we are still increasing the reverse voltage, so the intensity will be increasing, and hence more number of electrons can be pulled out from the valence band, and hence more number of minority charge carriers can be crossing the junction, and which leads to more current. And at one point, the depletion region will get vanished, and hence more number of charge carriers can cross the junction easily, and hence the current can be increased rapidly. So this is how the breakdown is happening. So in heavily doped PN junction region, as the depletion region is narrow, the electric field intensity across the depletion region is very intense, which can pull the electrons out from the valence bands, and hence more number of charge carriers, minority charge carriers, can cross the junction, which increases the reverse current heavily. And again, at one point of voltage applied, so the breakdown of the junction occurs, due to which more current will be flowing rapidly, even for a constant voltage applied. So here, the one thing that we have to remember is, in a Zener breakdown, once it is happened, the diode can recover to its original position. Whereas in avalanche breakdown, once the breakdown has occurred, we cannot recover, the diode cannot recover to its original position. So here, the original position of diode can be regained by just removing the reverse voltage applied. So simply by just removing the voltage applied, the diode can go to its original position. That means we can use that Zener diode again normally, whereas the PN junction diode cannot be used once it has breakdown. So let us observe the characteristic curve which is showing the avalanche breakdown and Zener breakdown. So here, in case of lightly doped diode, the breakdown occurs little late than the Zener breakdown. So here, this is the avalanche breakdown which is happening at more reverse voltage applied, whereas Zener breakdown is happening earlier than the avalanche breakdown. That means in heavily doped diodes, the breakdown occurs for a smaller amount of increase in the applied reverse voltage. So these are the reverse characteristic curves, and in which we can observe the avalanche breakdown and Zener breakdown. Let us now discuss the comparison between avalanche breakdown and Zener breakdown. So as we already know that this depletion region, so avalanche breakdown occurs in lightly doped diodes, whereas Zener breakdown occurs in heavily doped diodes, and hence the depletion region is thick in case of avalanche breakdown, whereas in case of Zener breakdown, the depletion region is thin. And here, once the avalanche breakdown has happened, the junction destroy, whereas in case of Zener breakdown, the junction will not destroy. It can gain its original position by just removing the applied voltage. So electric field, as we have thick depletion region, the electric field intensity is less, that means weak in avalanche breakdown, whereas electric field intensity is strong in Zener breakdown. Coming to the doping concentration, so avalanche breakdown happens in lightly doped diodes, and hence doping concentration is low, and Zener breakdown happens in heavily doped diodes, and hence this doping concentration in Zener breakdown is heavy. And temperature coefficient, it is positive temperature coefficient avalanche breakdown, whereas Zener breakdown is negative. So that means here the breakdown is happening due to the thermal energy, whereas the breakdown is happening due to the high electric field intensity near the depletion region. And the ionization is due to the collision, whereas in case of Zener breakdown, the ionization is due to the high intensity, high electric field near the junction. And breakdown voltage is directly proportional to the temperature. If the temperature increases, breakdown voltage also increases in case of avalanche breakdown, whereas it is inversely proportional to the temperature in case of Zener breakdown. So as I told you already, after the breakdown, voltage will vary slightly in case of avalanche breakdown, whereas in case of Zener breakdown, once the breakdown has occurred, there is a rapid increase in the current for the constant voltage. So that means voltage remains constant even after the breakdown. So due to the property of voltage remains constant, okay, due to this property, this Zener diode can be used as a regulator. Zener diode, that is heavily doped diode, can be used as a regulator. So that is a major application of Zener diode. So that means here always we operate the Zener diode under reverse bias condition, and which can be used for the voltage regulation applications. Thank you one and all. That's all for today. I hope it is clear to everyone. In this lecture, we have seen load line analysis and temperature dependence of VI characteristics and breakdown mechanism in PN junction diode. So I hope it is clear. Thank you one and all.
Like, share and subscribe. Hit the bell icon for more updates.